Stoichiometry are means of quantifying things in chemistry. What is stoichiometry? Stoichiometry is a mass relationship between different things, either between different elements in a compound or between different compounds in a chemical reaction. We have composition stoichiometry and reaction stoichiometry. Composition stoichiometry relates to the relationship of the elements within a compound. Reaction stoichiometry relates to the numbers and quantities of elements and compounds in a chemical reaction between two different types of compounds. All of stoichiometry is dependent upon the unit of the mole. The mole is just like any other count unit, like a dozen, where a dozen is 12 things. There are 12 things in a dozen. 6.022 times 10 to the 23rd is the value of the mole. So in a mole, there are 6.022 times 10 to the 23rd things in a mole. The mole allows us to relate apples to apples, as it were, because in any sort of chemical process where we're dealing with different elements and different compounds, every element has its own unique mass. And the different masses of different elements prohibit us from being able to relate things easily on a mass-to-mass scale. We have to convert masses into numbers of moles first, because moles are counts rather than mass, and they equilibrate the number of particles overall. We can use a mole to relate how many particles there are in a substance based upon the mass that we can weigh. So we use stoichiometry in order to quantify things, and we create ratios of different substances in order to do dimensional analysis on our process. So if we take an example of a chemical reaction like this combustion of octane, we have a mole relationship between each of them. There are 2 moles of octane, the first compound, 25 moles of oxygen, molecular oxygen, the second compound, 16 moles of carbon dioxide, the third, and 18 moles of water, the fourth. So for every 2 octane, there are 25 oxygen, 16 carbon dioxide, and 18 water. We can create a ratio then of 2 to 25 to 16 to 18, and any 2 of these 4 things can be related against each other. 16 to 18 CO2 to water, for instance. Compare any of them. If we take octane versus oxygen, we have 2 to 25. We can create a conversion factor from this pairing such that we can go from oxygen to octane by taking a conversion factor of 2 to 25, or from octane to oxygen by taking a conversion factor of 25 to 2. We can establish mole ratios in this way that allows conversion from one thing to another thing, A to B, generically speaking. So if I wanted to go from substance A to substance B, if I weigh a certain mass of substance A, I have to go from that mass of A into the number of moles of A in that mass. Once I have the number of moles of A, I can convert from moles of A into moles of B. And then I can find out how much mass that would be by going from moles of the substance B back into its mass. I use molar mass to convert between the mass of A and the moles of A, the moles of B and the mass of B. So going from mass to moles, or moles to mass, I will use molar mass. In order to go from moles of substance A to moles of substance B, I use a mole ratio, where it relates how many moles of each there are in the balanced chemical equation. I can use the definition of the mole, 6.022 times 10 to the 23rd, to convert from moles into particles if I would rather go into a number of particles rather than into a mass. So looking back at the same example of an equation, how many moles of oxygen would be needed to react 16.5 moles of octane? The ratio of octane to oxygen is 2 to 25 in the balanced chemical equation. We can use this to set up our conversion factor. There are 16.5 moles of octane, and for every 2 moles of octane there are 25 moles of oxygen. I put the octane, what I have, on bottom. I put the oxygen, what I want, on top. The ratio is 2 to 25, so 2 goes on bottom, 25 goes on top. When I multiply it out, I wind up with 206.25 moles of oxygen to completely react all 16.5 moles of octane. We can relate moles to moles or mass to mass in this way. So if I want to go from 16.5 moles to 206.25 moles, I use my conversion factor like we just did. The reaction ratio is then 16.5 moles to 206.25, which accurately reflects our 2 to 25 ratio that we talked about here. In mass terms, 16.5 moles of octane weighs 1,885.29 grams. 206.25 moles of oxygen weighs 6,599.75 grams. So we have a ratio of 228.52 grams to 799.97 grams. Usually, we will use reactant versus product in stoichiometry because normally what we're looking at is how much of a reactant that will produce a certain amount of product, or how much product I can get from a certain amount of reactant. But we can also look at different aspects within a reaction as well. So the sequence then, stepwise, to go from one thing to another thing. If I was looking at my octane, if I have 1,885.29 grams of octane, and I want to convert that to oxygen, I would convert from mass into moles by taking the molar mass of octane. Since molar mass is represented by grams per mole, I already have grams. I want grams then to go on bottom in my conversion factor. So I put the 114.26 grams on bottom, the 1 mole on top. When I multiply across, my units cancel, leaving me in moles with a value of 16.5 moles. I'll take that 16.5 moles then and convert from moles of octane into moles of oxygen using my mole ratio of 25 to 2. 16.5 times 25 to 2 will give me 206.25 moles of oxygen. If I take those 206.25 moles of oxygen, I can determine how much it weighs by multiplying by its molar mass of 31.9988 grams per mole, and that will give me 6,599.8 grams of oxygen. Altogether, we go from the initial mass of octane, converting by molar mass into moles of octane, from moles of octane into moles of oxygen, from moles of oxygen back to mass of oxygen. We can do this for any pair of substances in a chemical reaction. The limiting reactant is a concept in which most of the reactions we deal with will not be equal. It's a situation where the reactant amounts that I'm given are not equal to the reaction ratios, where I have more of something than I can use up based upon the reaction ratio. It's very difficult and very rare that we get exactly the right amounts of reactants for all of our reactants so that everything is used up and there's nothing at all left over. As kind of a crude example of this, more mundane, if we were trying to make hot dogs out of hot dog buns and hot dog wieners. If we had 8 hot dog buns, if you look at the left-hand side, count them up, there are a total of 8, and 10 hot dog wieners, we can make 8 hot dogs out of that, because to make a hot dog you need 1 bun and 1 wiener to make the hot dog. So if we put them together, because there are only 8 buns, we can only make 8 hot dogs. But because there are a total of 10 wieners, we have 2 of the wieners left over. So we're limited in the number of hot dogs we can make by the hot dog buns. The hot dog buns would be analogous to our limiting reactant in chemical terms. If I have 2 reactants involved and I have more of one than I do of the other in terms of my reaction ratio, I've exceeded the reaction ratio for one substance versus another. That substance is in excess. There's more of it than I need, just like there are more hot dog wieners than we need here. The other reactant is limiting. It is the one that determines just how much of the product can be made. And percent yield is another topic we talk about in stoichiometry, and percent yield refers to how much of a substance we get out of a reaction versus how much we expect to get. Oftentimes reactions are not 100% complete. They do not go quote-unquote to completion. Now there are a number of reasons why this can occur. And the reasons why they generally occur are because either we have, for some reason, the reaction just doesn't go to completion, it stops on its own. This often is due to a process called equilibrium, which is beyond really what we're going to talk about very much. Sometimes we'll form what are called side products, where side products are things where instead of making the product we want, the reactants form something else. And most commonly, we have a percent yield that is less than 100% because we lose some of our product when we're trying to extract it from our reaction mixture in what's called a workup. Now, the two variables involved in percent yield are the theoretical yield, which is based on our stoichiometry. If I have a certain mass of something, I can calculate how much of a product I expect to get out of that mass by the means we just did a little while ago. That gives us a yield that we expect to get in theory. The actual yield is the measured yield we get from finishing the reaction. So the percent yield will compare the actual yield and the theoretical yield. The percent yield is the actual yield divided by the theoretical yield multiplied by 100%. So for example, if I have an actual yield of 2,110 grams and a theoretical yield of 3,120 grams, my percent yield would be 2,110 divided by 3,120 times 100%, which would give me a 67.63% yield.